Good day, I'm Maile Madziba. Welcome back to our channel. We're continuing today with class test 3 of our CIR 123, which is the second chemical engineering module at the University of Pretoria. We're looking at part 2 of class test 3, and this is actually the 2011 version of the class test 3. So in part 1, they were saying, in part 1, which was A of the class test, they were saying that we should calculate the composition of R, and we did that. Now in part 2, which is B, it says calculate the mole ratio of the paired stream in relation to the fresh feed. So they want the mole ratio of the paired stream, which is here, in relation to the fresh feed. So I've put together a couple of steps, 4 steps in total to actually answer this question. So step 1, in step 1, we're going to be doing a mole balance at the mixer. Let me just write it down, that do a mole balance at the mixer. So this is actually the mixer. This is where everything mixes. So the feed and the recycle stream, and then we have the A exiting into the decomposition reactor. So I'm going to be doing a mole balance here just to get an important equation, which will be our first equation. And with that said, we can just say F plus R is equals to A. This is because, like I said, the feed plus the recycle stream equals to the A which exits into the decomposition reactor. But we have already been told that A, it's actually, we should choose 100 kilomole basis of A. So which means now we can simply just say that F plus R is equals to 100 kilomole per hour, and this will be our first equation. Now this concludes step 1, and we'll go to our step 2. In step 2, we're going to be doing a CH3OH balance at the mixer and then solve for F and R. So let me just say, do a CH3OH balance at the mixer and solve for F and R. So in our step 2, we're going to be doing the CH3OH balance here. This is because we already, from the first part, we already know the composition of R. We know how much percent, we know the percentage of CH3OH in R, and then we also know the feed stream, and then we also know in the feed stream we are told that it's actually 98% of CH3OH, and also in A we are told that it's actually 85.4 kilomole of CH3OH. So with that said, we can actually do a CH3OH balance here to get the second equation, and we'll have 2 equations and 2 unknowns, and we're going to be able to solve for F and R. So with that said, we can just go to our step 2. We can just say that 0.98 F plus 0.8144 R is equals to 85.4 kilomole per hour, and that becomes our second equation. That is to say, all of the CH3OH here plus all of the CH3OH in R, which is, this is still R also here, all of the CH3OH here and all of the CH3OH here is actually equals to all of the CH3OH here. So we just did that balance, and doing further simplification, we can just take it to 0. Therefore 0.98 F is equals to 85.4 minus 0.8144 R. So I just rearranged and put everything in terms of F. I took the R the other side, and if you do further simplification, you'll find F equals to 85.4 all over 0.98 minus 0.8144 R all over 0.98 as I divided through by 0.98, and therefore F is equals to 87.1 0.1428 minus 0.831 minus 0.8310 R. I can name this the third equation, but it's basically the second simplified, but it's easy to work with this one. So with this said, now that we have found we have two equations and two unknowns, remember in our step one we have the equation here in terms of F and R, and we have another here in terms of F and R, so we can just do simultaneous and solve for F and R. So with that said, we can just say substitute 3, which is this one, in 1, which is this one, and if you do that, you will find 87.1428 minus 0.8310 R plus R is equals to 100. Therefore, when you simplify further, 0.169 R is equals to 100 minus 87.1428. So that's basically how it came to be. So to get here, I just took all the F and I substituted it here and I got here, and then I simplified. In simplifying, I minus the R and I put the other, I send the one the other side. And then with that said, then it takes us to 0.169 R is equals to 12.8574. Therefore, R is equals to 76.08 kilomole per hour. So this is actually R here. So now we know how much R is. So when we know the R, it's easier to actually calculate the F. Why? Because remember, we have the F here in terms of R, so we can just move further to say from equation 3, F is equals to 87.1428 minus 0.8310 multiplied by 76.08. Let me just bring it here. So this is actually equation 3. What I did, I just took R and I actually substituted it I took R and substituted it in equation 3. Or let me just say substitute R in 3. Right? I think it's easier that way. But either way, it should be much more clearer. So with that said, if you use your calculator, you get F to be 23.92 kilomole per hour. So now we have R, we have F. Well, we didn't really need F for the equation, but we didn't really need R to answer the question, but we needed it to calculate F, because F is very much necessary and important. It's crucial for us answering the question. So now that we have F, it concludes our step 2 and it takes us to our step 3. So in step 3 we're going to be do a C6H14 balance of the whole system and calculate P. So now that we have F, we're going to be using C6H14 balance, and then in the whole system this time around, we won't do it in the mixer. We're going to be do a C6H14 balance in the whole system and calculate P. This is because if you actually started in the first part, you'll realize that C6H14 is actually a tie compound, because all the C6H14 that comes here exits here. And we are told, there are a few things we need to remember, that C6H14 we are told it doesn't react and it doesn't interfere with anything. And also from the first part we calculated D, we know that in the separator only CO and H remain gases and they be discharged through D, and everything else, all the other gases become condensed into liquids and then they come down here. And part of that is being patched. So which means C6H14 is only coming in here and exiting there. Unlike CH3OH, which part of it react and it lives there. So if we're going to be using C6H14 as a tie compound, it's going to be much easier because we can easily relate F and P using C6H14, especially because in P, in the first part, we already know the composition. We already know the percentage of C6H14 in P. So with that said, this takes us to actually our step 2. So our step 3 rather. So we can just say C6H14 balance. Let me write in bracket, it's important. Whole system balance, right? We can just say 0.02 F is equals to 0.1856 P, and this becomes our fourth equation. This is because already we know that C6H14 is a tie compound, right? There's 2% of C6H14 here, and also from our first part we calculated that there's actually 18.56% of C6H14 in P. So we can simply say all the C6H14 here is equals to all the C6H14 there, and that's basically what this equation is saying. So with that said, we can say therefore P is equals to 0.02 F all over 0.02 F all over 0.1856, right? So now if you're going to be substituting, remember we have P in terms of F, but we already have calculated F here as 23.92. We can just say therefore P is equals to 0.02 multiplied by 23.92 kilomole per hour all over 0.1856, and therefore this gives us P is equals to 2.58 kilomole per hour. So this is basically now our P. Going back to the sketch, we now have the F and we have the P, and the question is saying that calculate the mole ratio of per stream in relation to the fresh feed. So now we can go to this, conclude our step 3, then we can go to our step 4, which is the last step. Step 4, we can just say calculate. We're then answering the question directly because we have all the information we need. Calculate the mole ratio per stream in relation to the fresh feed, right? And therefore P over F is equals to 2.58 kilomole per hour, which is our P here, all over 23.92 kilomole per hour, which is then our F. Which is then our F here, and we did calculate that. So or should I bring it? Where's that F? Oh, sorry. Yeah, this is the F. We did calculate the F here as 23.92, and if you use your calculator, that gives you 0.1079 or 0.108. So this then brings us to the end of our part 2 of CRR 123 cluster 3 of 2011. So thank you for your time, and I hope we meet again in our next video.